Yeah, hopefully it's working. Slide that guy down.
You can hit the X on the invite people.
Oh, can I? Look at that. Look at all that extra screen space. All right, so like I said before, we're going to talk about a little bit more 3D. I think you guys would appreciate a code sample. I'm going to have to remember how to do all this stuff. I have to look it up almost every time, but it's generally the same thing. We'll test your memories.
It's not going to be a fun test.
Yeah, well, we'll see. We'll see if we can do it together. Group talk. Okay, so last time we talked about intelligence, artificial intelligence. So hopefully you've there's a pretty good read, pretty good chapter in there. It's actually broken into two sections, 5.3 and 5.4. If you want to start looking at that, and then also if you want to see how professionals do it, there's an article that's right here. This will not be on the exam. You don't have to read it, but it's an interesting insight into how simple some artificial intelligence really is. Okay. So today we're supposed to really talk about character animation, and I think I'm going to postpone that so that we can talk more about 3D graphics, because if you look down here, as promised, things are starting to slow down just a little bit. We see that there's a 3D graphics assignment. Notice there is no meeting time next week. Now, is that true?
Yes.
Well, for you.
If you're working on a solo project, that's true. I'm expecting that you're using this time because if you look, right here is the alpha game prototype. Use this time to do those three things that you said that you were going to do in your project. Remember, your project is worth 30% of your grade, so if you're trying to just come out with the largest grade possible or the best grade possible, then you want to devote some time to that and try to get some extra credit. Try to integrate some of these things that we've used, like particle systems and whatnot. Some of them are required, but that's an opportunity for you. Okay, so let's get back into 3D graphics and finish this out. See where we last left off. Okay, this is generally where we left off from what I remember. Yeah, let's go right here. From current slide. Okay, so we had talked. In fact, it's a little bright in here, isn't it? You want to kill just one of them? I'm afraid if you kill both, then people will fall asleep. I would fall asleep if I were in my class. Why? And it's okay to yawn in my class, by the way, too. A lot of people are so polite, they're going, so I see all these kinds of things. It's cool, just yawn. It's not going to hurt my feelings. I took a class, I kid you not, one time I think it started at 10 p.m. At Georgia State. It was just one of these really super late night classes, and everybody was drinking coffee and trying to stay awake, and it was tough. So yawn away. Doesn't hurt my feelings. And now everybody's like, well, now I feel like I have to yawn. Yeah. Is it possible to reverse the lighting? Let's see.
Reverse lighting.
Is that better? Hey, very good. All right, good idea. Yeah. All right, so when we talk about computer graphics, you know the major phases of the graphics pipeline. How many people studied that for the exam? Said for sure this is definitely going to be there. Okay. Yeah, I'm sorry. I can only pull one graphics question, and there you go. But anyway, when we're talking about that, how do we render characters? I don't know if we've discussed this in detail, but I pulled these things. I used to teach the 3D modeling and animation class. I don't know if you know about this one, but it's the CGDD 4113 class. It's specifically for games majors that want to go down the media production pipeline kinds of things. And so they have to build a dog in this class. And so if you're interested in that, you will probably be building a dog when you get to 4113. Looks like this. It will not turn out like this unless you have some serious skill. Everybody's dog that they turn in is the most foobar dog you've ever seen. The ears are all over the place, the face. Those are really tough skills. Even if you're a good 2D artist, it doesn't necessarily just go straight in and transcend into 3D. So anyway, this is the one that came with the book.
Does that dog have thumbs?
Does the dog have thumbs? Yes, of course. And how many fingers does the dog have?
4.
I can't tell you. 4. It's actually 4. They always have 4. I don't know why they have 5. Is it Disney? Mm-hmm. Okay. I do know that in The Simpsons, there was a scene where God came down and talked with Homer.
Yes, but
and he has 5 fingers, and that was like a big deal, right? So, never mind. Anyway, moving on. So we have this mesh that is created. The question is, how do we animate this mesh? This is typically the job of an animator. Realize that we have people that have very specialized skills. There are some people who do nothing but build dogs, the mesh of the dog, or the mesh of a character, or the mesh of an ogre, something like that. They are modelers, and that's what they're responsible for doing. You would see these folks working at Pixar. They would work at SCAD and these kinds of places. But their responsibility is just to create the geometry of the character. What's the next person in the pipeline?
Create the model.
The people who do the rig. Now, what's a rig? You're going to hear that term a fair amount. Okay, it's the skeleton that you see right here on the inside of this. Believe it or not, you can put this skeleton-like structure on the inside of the character. That's only part of it. They also do things like putting constraints on what the skeleton can do and putting control handles on the skeleton and making it so it's really easy for an animator to work with this. For example, one of the things that we might do is to have the eyeballs focus on a point. I don't know if you've ever seen this, but you can move this point around in space, and all of a sudden the eyes are going to start looking at the point. Why is that so good for an animator? Think about if that wasn't there. What would the animator have to do?
Move the eyeballs.
They would have to individually adjust that, right? So there's a lot of things like that. Also, we work with something called inverse kinematics in skeletons. Now, if you don't know this, let's have a quick conversation about forward kinematics and backward inverse kinematics, okay? With forward kinematics, if I wanted to rotate, let's say, the joint, we've got this dog that's kind of standing out in this T-pose or something like that. Why do they stand in the T-pose like this, by the way?
It's easy to move the arms.
It's a good reference.
Or when you move
when you're making the model, it's easier to make the model for that sort of setup by looking at the top, the side, and the bottom.
That's partly true. But believe it or not, this is, well, that's true too. You can do mirroring and everything else, but this is halfway of the total flexibility of the character. I can go up here and come all the way down here. What about legs? Is this about halfway? Well, unless you're going to bend the leg all the way up and do some of these crazy things. Now, and that's why you see the character stand in this T-pose. It's because it's the best kind of halfway point of the total flexibility. So some of these things with regard to other constraints they put on it would be forward kinematics or inverse kinematics. With forward kinematics, think about what I would have to do. If I can rotate all of these joints individually, how might I do an animation?
Move them in conjunction.
I want you to think about how bad this would suck for an animator. What do animators do? They know how the human body works and how creatures work and all that kind of stuff, right? So what would they do if they could only rotate joints? Elbow joints and stuff like that.
rotate each one.
How would I do a punch sequence, let's say, just for the arm? What would I have to do? I'm like this, so what would the first rotation be?
Shoulder.
Because think about it, I want to get like this as my first punch. So what would I have to do? I'd have to rotate shoulder. So here we go. Okay, good. Now what?
Rotate
You can only
bend your
rotate
elbow.
one joint at a
Then
time.
elbow. Okay, now?
Rotate
Now rotate shoulder.
bend elbow.
Now rotate wrist. Okay, great. Now I've got that. Now if I want to go forward a little bit, what do I have to do?
Do it all again.
If you're not going to be moving forward, we don't want you.
No. I'm saying I want to go like this or what, like, it doesn't really matter. But what would I do?
Reverse it.
Okay, I'd start here at the shoulder. I'd raise the shoulder up just a little bit of rotation, and then what?
Rotate the wrist.
Rotate the elbow a little bit as well. Now think about how bad that is. What do animators really want to do? They'd like to be able to just grab the hand and say, your hand needs to be right here. You with me? So this whole process of moving the root joint, like a shoulder joint, then to the elbow joint, then to the wrist joint, and all that kind of stuff, that's forward kinematics. With inverse kinematics, you grab the end, it's called the effector, and you position it where you want, and all of the other joints up the hierarchy fall into place. That's pretty sweet. It makes you wonder how that's done. Fortunately, we have an assignment on how that's done. So you're going to understand it just a little bit better by the end of this. But I do want you to understand the difference between forward kinematics and inverse kinematics, because that's really a big deal, and animators use that term all the time. Okay, any questions about that? Right, so you have somebody who builds this rig, and they place it on the inside of this. Then what happens? You pass that off to who? Yeah, maybe a texture, maybe, it would be somebody who draws textures and things like that. But then it goes off to the animator. It's funny because I've hired animators. I used to run a lab, or not a lab. I used to run a shop here in Atlanta, and I had about 10, 15 artists. And I hired an animator. And I was surprised because the animator had no clue about how to build or rig a model. All they did was animate. And so their demo reel was of this thick person sitting in a bar, drinking. They were drinking beer after beer after beer, and then it's time for the character to get up from the bar, and they start stumbling like this, and it was the most realistic looking animation you've ever seen. It looked like somebody had done motion capture or something like that. That's all that this person did was drunk characters.
Well, he knew what he did.
It was a she, actually, but yeah, she was really good. But anyway, That's the process there. Now, once we have this animated skeleton that's going and everything else, what happens? The mesh is deformed according to the skeleton. And you can have some of these points inside the geometry that are affected by multiple bones. They can be affected by numerous things, but we're going to skip that for now. Okay, so continuing on the rendering side of things, think about how many polygons there are to render total. There's millions of polygons. Do we want to render everything? No. So we'd like to be able to cull some of the information that we're about to render out. What are some things that are immediately discarded? Does anybody remember?
Triangles facing the other way.
Triangles that are not facing the camera is a big one, right? You've probably seen this in some of the games when you go inside of a character that's, one of these giant ogres that you killed or something like that. It disappears because you're inside, right? There's no faces that are there. There's also some other things that
no faces.
we're not really going to get it, but the main idea is culling out some of the information. They have these things like portals. You can almost think of this as if you're looking out a window inside of a building, you can only see outside the window part. There's no reason to see. You can't see through walls, and so you can use these portals to call out the number of polygons you have to render. There's also these things called binary space partitions, and this is best if you look at it right here. Okay, I'm not going to walk through this whole algorithm, but you can imagine that if we're way over here, in let's say the left side of this cave system or something like that, and if I can't see, let's say, part of it over here, I can't see its children either, right? Let me say this. If I were going to dice this up and try to make some hierarchy like you see here, this tree structure representation of this, if I can't see anything inside of B, let's say in the second image, then there's no way that I can see E or D or any of the subdivisions within E or D. Does that make sense? So what they do is they create this data structure that says we're going to set up the major chunks of it, and if you can't see one of these really high-level kinds of things that has all of these polygons and all of these guns and all of these bombs and everything else, there's no reason to transcend that tree. You can just go down, transcend? No. Traverse, thank you. To traverse that side of the tree, right? You can't see the parent, you can't see the children. That's the main idea. Yes?
Isn't it because of floor optimization this can happen where it just pops in, like the character will quickly turn to the right or to the left and do something that was called out of this that would have to wait a little bit for it?
I could see that it could be possible. Depending on where it is, maybe if it's between two different major categories or something like that, two major sections of territory that might happen. I don't know. Okay, so moving on. There's also things like this. There's quad tree partitioning, and that looks like this, right? So if I want to divide up a territory that's square, what can I do? I can start chopping it into quarters and chopping that into quarters and keep chopping that into quarters. And there's different ways that we can represent this with bits, such that, for example, this whole thing right here is the entire terrain, let's say. This quadrant here is 0, 0. This is 1, 0, 0, 1, and 1, 1. Right? So if we look at it as 4 different possibilities, I could do that same thing here with the upper quadrant and everything else, and I can actually use bits to represent where something is inside this quad tree data structure. Main idea here is that we can divide this space into something that's hierarchical, and we can be clever with how we access certain parts of the terrain. Yeah? Yeah, you can read the book on that part and figure out how the algorithm works. Because I know everybody's going to read the book. Can't wait to find out the answer. In fact, we'll talk about it at Siege for all of you who are going. We'll just start talking about quad tree visualizations.
Have a book club.
Oh, that would be great. That'd go over really well. No, maybe not. Okay, a couple of different things that you're going to see when you get into a graphics class are the primitives that you can render. So the way that you can render these things. We might have a triangle list. Now, what do you suppose this is?
A list of triangles.
Duh. It's a list. I haven't used the word duh in a long time. There you go. It's a list of triangles. So literally you say, here's triangles, 1 point, 2 point, 3 point. That's one triangle, and then the next 3 are another triangle, and so on. So we have a triangle list. Now, is this optimal? No. And I'll tell you why. Because a lot of times when you have a mesh, in fact, if we go back here to our dog, and if I look closely at the dog, and I'm looking here at the chest, I see a point here. How many triangles share that point?
2, 4. Oh, well, a lot.
At least 4, right? And think about how complex a human face is, right? So you can have a whole bunch of triangles that are all using the same vertex. Do you get that concept? Okay? So why is a triangle list so inefficient? Not only are you storing more vertices that are duplicated, you're also having to do the math on all of those things. Let me say that again. So you're wasting memory because you're storing redundancy there with all these extra points, but you're also having to process that, right? We're having to do all this matrix math and everything else, and you're easily doubling, if not quadrupling, the amount of stuff that you have to translate. Let me draw up a picture. See some people that are not happy with me. Okay? Let's just show something like this. We'll work only with triangles. Okay? Is everybody cool with this, right? How many triangles for that point? Two. What about this? Two. What about this guy? Four. Okay, so we have 5 different vertices, and you can see that it's pretty heavily connected. Now, if I were to use a triangle list, the most inefficient way to do this, what would I do? How many triangles would I have? I'd have 4 triangles. How many points total?
12.
You guys can do math, right? You can see that there would be 12 points in a triangle list. Now, what if I was smart about this? I wouldn't re-specify this. I would only have 5. So how much of a savings do I get? About 50% of the original cost. You see? Does that make sense? So let's look at this. Watch this. Beautiful stuff. So here's our triangle list. There's something called a triangle strip. This is some pretty clever stuff. Watch what I can do. I can specify the first triangle. That's 3 points. You have no choice there. The next triangle, however, costs how much?
1.
1 vertex. And the next triangle after that? 1. And the next triangle after that?
1.
So you can see there's a huge savings that's associated with this as opposed to the triangle list. Why is this such a big deal? Could I take somebody's face and basically, do just a triangle strip and kind of wrap it up and down on their face?
Yeah.
Yeah, sure I could, right? It's not always going to be perfect, but you can see there's huge savings that are associated with that. There's also this thing called a triangle fan. I have used this exactly 1 time in my entire graphics career. Do you know what I was making?
A fan?
No, it was not a fan.
An octagon.
Human
Oh.
Yep.
The SPSU symbol. Okay, how does the triangle fan work? Well, you can see we specify this first point down here. There's 1, and then 2, 3, 4. Basically, we can make these. They're called fans for a reason. So it's like one of these. What kind of fan is that? Japanese
Paper fan.
paper fan. Okay, is that really? People know what it's called, the Japanese paper fan. But there you go. You really don't use that, but it's still an option because it's made out of triangles. We also have a line list and a line strip. What do you suppose the difference is there? You can see these segments versus this line strip. There's actually something called a line loop that, for whatever reason, is not there.
How would you store a triangle strip?
How would you store a triangle strip? That's a great question. What would this look like? It's a list of points. Okay. Yes?
What do you use the line? What do you use just lines for? Are called or not related? So.
Why would I use a line list? It's almost depending on what you want to do. Putting the pen down, drawing a line, picking the pen up, putting the pen down, drawing another line. Drawing a highway line, I don't know. Somebody help me out. I'm the graphics guy, and I don't know the answer to that. Again, I really don't use this. I use a lot of line loops, line strips, and things like that because if you want to render something in wireframe, you want to be able to see through it. You want to have some of those classic kind of visualizations. You can do that. Yeah, but line list, no, you're not going to use it. Okay, so here is a mesh as a triangle strip. We had already talked about this, so I'm just going to skip over that. You can see we could make a face or something out of that. Okay, now going back to this optimization, we have a couple of different buffers. If you haven't taken the graphics class, please pay attention. This is the most difficult thing you will learn in computer graphics, at least at the entry level that most of you guys are going to go in. We have a couple of different buffers. Now, we're not talking about the frame buffer. What is the frame buffer? Let's have a review of terminology. Frame buffer is?
It draws the thing before you.
It's what you see. It used to be in the old days, and Ross, maybe you've done some of this too, and I'm not pointing you out. You could flip your monitor, you could flip your graphics card, and you could actually have direct access to the frame buffer. And you could say, you know what, this is just a giant array, and you could start saying, okay, the pointer here, and with an offset of 500, I'm going to change it to the value 75. And believe it or not, one of the little pixels on the screen would turn a different color. You're like, heck yeah, right? And you started looking about how you could do line algorithms, and you started building your own graphics, in the really early kind of phases. That's not what we're talking about. Frame buffers, you still have them. You don't have as much access to them. We also had a double buffer, like an off-screen buffer. What was that used for?
Switching out.
Yeah, that was used for switching when we're doing graphics and animation and interactive graphics and things like that. That is not at all what we're talking about. What is a buffer in this sense? Buffer is a term that people don't like to talk about. You know what a buffer is?
Something in between.
What data structure is it? It's an array. You're going to hear this term. I'm trying to prepare you. Computer scientists, software engineers, everybody's going to hear that a buffer is only a chunk of memory. That's all that it is. Okay, so it's an array. You have access to it. Now, there's two different kinds of buffers that we work with a lot in computer graphics. We work with a vertex buffer. What do you suppose we put inside a vertex buffer? The vertex information, the position information. Okay, so when I take a model and I'm pulling all of the points out of file, I have to push them into a vertex buffer on the graphics card. So everybody get that process. That is going to be something that's going to be difficult for you. You're like, hey, Jeff, I could just manually use a for loop. No, it's not the way it works. But the concept is that you're taking data points, position points of the original local space, and you're putting them on the graphics card. The next one is something that's an optimization buffer. Okay, it's called the index buffer. Now let me show you something. In fact, did we talk about it? I'm going to draw up something. Should I draw it into the lecture? Can I? What do I do?
Pick up a pen.
Pick up a pen.
Oh, yeah, that probably works.
Wait. There we go. Okay, we'll try it. All right, so, and hopefully it's in line. Okay? So, watch this. If I have, that's pretty good. Oh, it's down below. Okay, so that's why I can't see it. There we go. How many points do you see?
6.
Using a triangle list, what could I do with this? Well, really not a whole lot. Okay? But here's what I'm going to do. I'm going to say that that's 0, that's 1, that's 2, that's 3, here's 4, and there's 5. Right? So we have a total of 6 vertices that are with me.
Yes.
So here's the cool thing. If these are already on the vertex buffer, this is the first phase of the whole graphics pipeline. They get rotated around and they're in the correct spot in, let's say, the camera coordinate system. You with me? Right? So we've done all of the math. Now, what's the next phase of the graphics pipeline? We have to make some triangles. Do I have any triangles at this point? No. I only have vertices that are on the screen. Or no, you can't even see them on the screen because they're infinitely small. So then what the index buffer says is, here's how we're going to hook them up. I'm going to make a triangle between 0, 1, and 3. I know it keeps going downstream. 1, 2, and 4. And then 5, 3, 5, 3, and 4. This is our index buffer right here. I don't know why it keeps doing that, and I don't know what language that is. There you go. Okay? It looks kind of cool.
It's a cartoon face with a
It looks
nose.
like an ear.
Yeah. Yes.
What do you guys see?
A nose.
A nose? It doesn't matter. This is our index buffer, right? So it's just a series of numbers saying if you're going to construct these triangles, watch what we're going to do. The first one is 0, 1, 3, so it's connected dots, right? 0, 1, 3. Here's my first triangle. 1, 2, and 4. 1, 2, 4. And then 5, 3, 4. And what do I have?
A triangle.
In fact, this is one of the labs that you go through, because if you can understand this, you understand that there's a vertex buffer that says, hey, the vertices are here and they've already been spun around in space and everything. Your index buffer is the one that actually connects the dots. Does that make sense? If you understand that conceptually, it's going to be a lot easier when you go into the graphics course. Now what do I do? Can I kill this? Yeah, good. Okay, so one of the last things that we need to talk about is texture mapping. Now, what is texture mapping? You've probably heard this term 1,000 times. What is it?
Mapping textures.
Mapping textures. Yes. Try again. The reason that I closed my eyes and scoffed was because some of you will be tempted to write that on the final exam. What's the problem? Let's talk about good test-taking skills. What's the problem with that? It shows no comprehension of, I know you understand it, but it shows no comprehension, right? So what is it that we're really doing? Redefine it in a different way. What are we doing?
Putting texture on.
Applying an image, for the most part, or a texture, to geometry. Why do we do it? So that it looks better, right? So we have a couple of different things. Believe it or not, we have 2D images, and these are the things like bitmaps and everything you've worked with, but we also have 3D images. What are we talking about?
Like terrain.
Volumetric data.
I don't like clouds.
Yeah, it's like a cloud. What are we talking about here? CAT scan, ultrasound. Right? So you can get into you can do all sorts of funky stuff, but you can actually have a 3D texture, believe it or not. Okay? We can also do things like cube mapping. We're going to skip over that for now. Okay? Vertices are going to have, therefore, additional information. Not only are they going to have position, but they're also going to have a place to where they map back into the texture, and that's called a texture coordinate. Let me say that again. In addition to having a position, an X, Y, Z, they have a UV coordinate that says where inside the image it maps to. Yes?
So that applies to, that doesn't just apply to Maya, it applies to other.
That's how texture mapping is done.
It's all called UV?
Well, the actual coordinates are called S and T, historically, and then they said, okay, let's talk about UV coordinates. I don't know why there's a difference between ST and UV, but they're the same thing.
I'm actually in 4013 class right now.
Oh, you're in graphics right now?
Yes.
Oh, good luck.
It's so far
Did that help?
No.
Okay, good.
It really hasn't been that hard.
Never mind. Okay, so what you need to understand then when you get to this point is that vertices are going to have a whole bunch of things. Everybody thinks that a vertex is just a position. Not true. A vertex has a position, yes, but it also has a normal. What's a normal again? Something perpendicular to a plane, but it can have a normal that kind of points in any direction. In fact, we're going to talk about that. That's really fun.
It can be perpendicular from any direction.
I'll show you things that you can do with it, and it's going to be mind-blowing.
Mine exploded.
Mind exploding. Okay. And then UV coordinates, right? Those are the texture coordinates. So how does this work? Here's an example. I have this Walmart smiley face, and I want to apply it to some geometry. Can you figure this out on your own? What do you suppose is going to happen? Couple of things to notice. First of all, these are not the position. 0, 1 is not the position. It's the UV coordinate. It's not an XYZ position. Remember, working in 3 dimensions. Here, it is a 2-part thing because it's a 2-dimensional texture we're working with. So what's going to happen is means that we're going to map this point, this upper left-hand point, to the upper left-hand part of the texture. The same thing is true right here. 1, 1 is going to map to the upper right, and you go all the rest of the way. The rest of the way around the polygon. So we get this. Any surprises? Hearing none. Moving on. What if we do this?
It stretches.
This is cool because as we stretch the polygon, because we haven't changed the UVs, what's going to happen? It's going to stretch that polygon. Believe it or not, you can do some really interesting things here too because the UV textures here that we have, the texture coordinates, you can change those. If I start to change the UV coordinates, what's going to happen? The texture actually is going to start shifting in all these weird ways on the polygon. Have you ever seen that before?
Yeah.
You ever look down at the water?
Yep.
In a game? What do you see? Yeah, you see reflections and stuff like that, but what else do you see?
Distortions.
You see, well, yes, you see distortions and all these kind of things, but you also see a lot of times textures that are moving across, right? Yeah. This is how they do a lot of water effects. And we're not going to talk about water effects, but that's how it's done. Okay? What if I do this? What if I change the texture coordinates so that it's no longer bound by 1, now we're at 2?
Nothing's going on.
The question is, if that's the case, where does 0, 2 map to? Where does this texture 1, 1 thing map to inside this polygon?
2, 2.
It's actually the center of the polygon. So what are we going to get? Well, depending on what options you set, you're going to get this. Now, why is this such a good feature? Why is that so cool? Yes, tiling. What do we do with tiling?
Save art.
Wallpaper.
Yeah, you could do wallpaper, but
Sprite sheets.
sprite sheets, yeah, you guys are dancing around it. What might we texture with this? Terrain, absolutely. In fact, if you look and somebody's done a poor job doing terrain textures and everything else, what are you going to see?
Black and white.
You're going to see these creases that go down. And I used to do that. I used to abuse that all the time in games because it would tell me which way was north, south, east, west. I would never be lost because I could look down and see the seams inside the texture on the terrain, right? So if we do something like this, if I wanted to replicate this thing 1,000 times, what would I do?
Just make the destination rectangle.
Right? I would just change these texture coordinates to 200, 200, something like that, and all of a sudden I'd have all these little smiley faces all over the ground. So what do I need to create a realistic plane of graphs? 2 triangles. Think about why, right? I can stretch this thing out as big as I want. I can scale this monster kind of 5-mile plane, and then it's just a matter of changing the texture coordinates so that we're stamping this grass texture onto the plane. Make sense? Good. Okay? What about now?
Wraps around.
You stare at it till it goes away. Yeah. That unfortunately doesn't work. It has not worked yet for me in life.
I know how you do it, how you change it so it has an eyes that actually have like a face on the side.
Okay, so there's a couple of different ways that we can do this. In fact, I don't know if I actually mapped it there. It depends on how the modeler set this up. Are you ever going to have to set texture coordinates? Chances are no. Unless you really know what you're doing in Maya or Blender or something like that, you will not be the person who maps the texture to the geometry. You can assume that this might be something like, you ever seen a globe, like a sphere, something like that, and they wrap it around? So all of this information at the top of this image might map to the North Pole. All of the stuff down here at the bottom might map to the South Pole. What about the section here in the middle?
The period of the sphere.
It goes all the way around the equator. That's just one option. It can be mapped 1,000 different ways. It depends on it. Yes?
Is that why in Unity that some things are materials and they're like sphere shape? Materials,
Yes.
Like with water, I know they have like that.
There are default texture kind of coordinates that you can assign to objects. If you have an object that doesn't have one, let's say you have a character that's in the T-pose, you can actually take the texture coordinates of this and map it to the character, and it would look stupid, but it would still work. You'd have noses and everything all over the place. So how do we do this then? Right, so if we're going to try to animate a character, that's what we're ultimately going after. We have to put a texture onto a character. How is that process done? Maya, right? Honestly, again, you don't do this programmatically, but actually kill the lights real quick because you guys will appreciate this. Look at the process that's going on here. You have this geometry of the character that somebody made this thing right there. Somebody later then added in these extra details here of the face, draw, all that kind of stuff out. And here's the texture map down below.
Yeah, the texture map looks nothing.
You might have seen stuff like this before, and it's disturbing. You know why?
Yeah, because all the things are.
They've unwrapped a human being.
Yeah, like that's basically it.
And it is creepy because especially when you start to see the face, you'll see the face and it's all pulled out on the texture and everything because this texture is mapped somehow to the geometry. If you're interested in how that's done, again, take the 4113 class and you'll get into all of that kind of stuff. Okay, you get into planar mappings and all of these kinds of things. Okay, but this is generally what goes on, right? So here's the texture map, and somehow magically all of these points map back to this texture. All right. We can do also some other things that you're going to hear. You have something called point sampling that we won't really talk about. There is this term called bilinear filtering. So what happens if you have a couple of things mapped to multiple points inside of a texture and things like that? Don't worry about it. MIP mapping, though, is pretty important. With MIP mapping, what we're saying is that we take half the size of the original texture. Here's an example. I pulled this off of Wikipedia. You have this satellite picture that might be a billboard or something way out in space. And then I take half of that size and stamp it right there, and half of that size, and half of that size, and half of that size. It's going to make it so it transitions a lot smoother. This is basically just a way to keep things from looking really bad. There's also this trilinear filtering. I'm not going to even talk about it. It's a graphics class. Okay, lighting. 3 primary parts of lighting. Let's see if we can identify these things. This upper left-hand image looks like a racquetball.
Racquetball lighting.
Racquetball lighting. No, it's not called that.
I believe
Diffuse.
It's called diffuse lighting. Okay? Now, there's some really interesting things that are going on in this room we're going to talk about.
lambda.
There is this guy right here.
Specular
It's called, this little highlight's called the specular highlight. Why is that so important in computer graphics? What does that tell us as human beings?
There's
a shiny
light source for them.
It's a hard surface. or it's a water surface or something like that. But we start to infer information about this object just because we see this little specular highlight. The smaller it is, what does that mean?
The less.
The harder it is, right? So you can imagine that if this was glass versus if it was a racquetball, something like that, the presence and absence of that specular highlight means something to us. Now, I want to creep you out again. Let's see if I can stand in a good spot. Is my face lit?
Yes.
Okay. Believe it or not, me standing here and my face is lit, I'm lighting your face. Would you agree with that statement?
Yes.
How much am I lighting your face?
Not
Very rarely.
Okay, the lights are currently off. The online people, of course, can't see that. But the lights are off. Are you being directly illuminated by anything? How is it that we see in this classroom? Okay? Things are bouncing all over the place, right? You have light coming in through the windows right there, but we still have blinds down, right? Me holding my hand right here, this thing becomes a light source. Now, in real time, can we compute that? No.
No.
No, we cannot do it. So we have to make a lot of approximations in computer graphics. Right here, it's very hard to see, especially in this slide, but if you look at the bottom one, there is a little bit more light that's in that scene. And you can only see it in the spots that are totally dark. This is called ambient lighting. Now pay attention because you don't want to have to try to approximate all of the physics that goes on in the real world. I always add a little bit of light into the scene. Do you know why? Why would I always want to have just a little bit of light added into every scene, no matter what?
Because it's so that you're never looking at something dark.
What does completely dark look like?
Black.
Bad. It looks bad. There is no such thing as completely dark ever, anywhere.
Unless you're in space.
Unless you're inside of a lead box or something like that, which probably doesn't happen to. You're not going to make a game about a lead box. Hey, buy my new game, lead box.
You can't see any.
So it typically looks bad. So what we do is we add in just a little bit of light to simulate situations like this what we have right here. Right? Notice there's no direct light source on anybody except for me right now. Yet you're still all illuminated. You can still see. Even the darkest spot down here in the darkest corner, you can still see there. Okay, so that's called ambient lighting. Do we need to talk about the major ones there? What are they? Diffuse? What is diffuse? It's the way that light falls off of the object, right? What is the next one? Specular, which is what?
Conveys
The shininess of the object, right? And then the third one? Ambient. Why do we have ambient?
so it's not all black.
And yeah, so it's not all black. And then technically there's one called emit. If you look at some of these things right here, it doesn't really emit color. It doesn't it's not like it's a light source. But you can just say, you know what, I'm going to make it look like it's glowing. And you just jack up the emit and the thing makes it look like it's glowing. It's kind of silly. Okay, we talked about modeling. You're not going to do this. And I hate to say it, unless you have real skill, you're going to suck at it. Don't even bother. That sounds really negative and stuff. If you take it, I've taught 4113 3 or 4 times. I have yet to see somebody who really does something. A couple of their own projects turn out to be pretty cool, but trying to make that dog, it's just the worst thing. So chances are you don't have these skills, but you can see there's a lot of subdividing polygons and everything else, different approaches. Okay. And then the last thing I think that we're going to talk about right now before we dive into some code, we talked about the fact that each vertex has position, it has a texture coordinate, and it also has a normal. Now watch why this thing is so fun. You can abuse these things. Okay? If I were to hold a triangle up right here, in fact I'm going to hold my hand up and imagine this is a triangle. You can see it. Why? Light source right there. The projector is casting light onto my hand. How much is it lit? It's fully lit. As I start to turn my hand away from the light source, what happens? Less and less light is hitting my hand, and it eventually turns, at 90 degrees, it turns completely unlit, assumedly, right? Is everybody cool with that? Okay, so there is a relationship between the normal of my hand aiming at the light source. So we've got a light source coming in this way, I have a normal coming out that way, and if they line up, then it's fully lit, and if it goes 90 degrees or greater, then it's not lit, right? Watch what we can do. Okay? We've got the geometry of this monster here in the upper left, and you can see if we put this shading on here by default, this is what it's going to look like with just diffuse lighting here in the second image. Everybody with that? What if I wanted to do this in the upper right? One approach that I could do, especially for these giant, divots here in the stomach and all that kind of stuff, is I could actually change the geometry. I could say, you know what, modeler, go out there, instead of making this thing right here, I actually want you to put the divots in there and all that stuff. Why would I not want to do that? Think about the extra polygons that I have to create to make these divots here inside the stomach. I don't want to do that. So what do I do instead? I change the normals of all of this geometry. How do I do that? I have something called a normal map, which is a black and white image. You can assume it's black and white, grayscale image, something like that, even though it can be RGB. It tells which way the normal space for a particular spot on this creature. So just like we had color information, right? Everybody's cool with that. Take a picture, you stick it over there. What if we didn't use it for color? What if we used it instead to say which way the normals were pointing? Aha! It's called bump mapping, normal mapping. Assume that they're the same thing in these two.
Bump mapping is different?
I'm not going to talk. Assume that it's the same for this class. There's a very fine difference between those two things. Esoteric, right? Okay, so imagine now we have this one flat polygon, and I have normals that are now facing in all these different directions. What do you think is going to happen?
The lighting is in a different way.
The lighting is going to be different for each little pixel that has a normal facing a different direction. What are we going to get? We're going to get effects like this monster right here with the divots in its thing. The geometry is exactly the same between this upper left and the upper right. It is the same geometry. But because we put a normal map on it and changed the direction that all the normals are coming off of the stomach, you can see the lighting effects that we're going to get. It's almost like that. Have you seen Hellraiser? The movie Hellraiser. There's a guy called Pinhead, I think.
Yes.
And he has all of these little pins coming. In fact, do I need to pull up Pinhead so you can hold on?
I have a question about the map.
No, hold on. We got to see Pinhead. Images.
Wait,
Oh,
Saints
wait,
are
that's not a
Saints
good
are
one.
done.
More repeatedly, but I still don't understand how that works.
Are you in the graphics class?
Well, yeah, but we haven't had the
You.
Is there any pictures?
Here you go. Here is the perfect example of normals. I know it looks stupid, but think about it. This pinhead, you've got all these normals coming out of the vertices that made up this guy's face, right? Now, what if we changed all of these normals so they were facing in all these different directions? You'd have a head, lighting-wise, that looks like it would have all of these divots and vents and everything else inside his head, just because it's a lighting trick. Does that make sense?
I'm gonna tell my kids that. When
So every time you're playing these games and you shoot a gun into something and you see that the metal deformed, did it really deform?
No, probably not.
No, probably not. And there's an easy way to tell, because if you look at the outside, imagine we have a sphere, and it's got all of these jagged things and everything else on it. It's all deformed looking. And if you look at the outside ring of that, you know what you're going to see? A perfect circle. Mostly perfect circle. But then the rest of it's going to look like it's all jagged and everything. Why? Because you haven't changed the geometry. Think about that. Great.
I didn't get it.
You didn't get that?
No, it's like we said that it's going to look like a perfect circle, but it's going to have a jagged.
That's the out.
Let me see.
Right.
Yeah, here, let me show you an example here, right? Here's exactly what we were talking about. In fact, we'll go from current slide. Where is that? Look at this. These two are the same thing. Do you see any difference? On the left, I'm sorry, yes, on the left, we have how many polygons?
Trillions.
Not trillions, but you have a lot of polygons that make up all the detail. It makes up all the geometry of the chest and every aspect, you know, every skin, scale, everything. And then you look over here, we've reduced it by probably 100 times, and we applied a normal map. Can you see any difference here?
There's a small difference, but it's basically
Yeah,
unnoticeable.
the horn, it looks a lot rougher.
But that's just a lighting thing. It's no different.
It's pretty darn close. Do you care in a game?
Nope.
You're being ripped apart by a minotaur or something like that. Do you care? Oh, look at that horn. Doesn't really look that.
too shiny.
Look, my intestines look a little funky there as I'm looking at the horn, you know. So yeah, it doesn't really matter. You use normal maps all over the place. Okay? Here's another example. On the left, 4 million triangles. On the right, 500 triangles using a normal map.
Same thing.
Which one's better, 4 million or 500? Yeah, clearly.
looks slightly better.
Huh?
4 million looks slightly better, yeah.
No, the 500.
Can you see a difference?
No.
Yeah.
I mean,
It's
just
slightly
different-
darker.
It's just different, like, lighting looks. It's the same thing.
I think you can see a very, very little bit of a difference. But that's why we use these things. Look, here's the geometry right there. It doesn't look like a face at all. What makes it look like a face? Shifting the normals around.
That's supposed to be a face.
Yes, I think it's supposed to be a face. It's one of these Greek sculpture things, I think.
Oh, I see it now.
Let me show you one other thing real quick. I don't know if it's in here. I know it's in my 4,000. Give me 2 seconds to pull this up. Texture mapping part 2. Let's see if it's here. I want to show you one image. Here you go.
Yeah.
Yeah. This is bump mapping, normal mapping, right? What are we doing? We're taking this plane and we're shifting all of the normals around. This is a visualization of it. Now watch this. Okay? If I take these two things and map it to a sphere, here's the color. Well, we'll talk in just a second. It's siege. We'll talk at siege. Let's talk about normal mapping. Okay, so here's the color. Right, here's the image that we're talking about. And then right here is the normal map. So we get something that looks like this. Can you tell there's a normal map on it? Nope. Be careful, can you?
I can see people.
It does look pretty scary.
Where do you see the normal map? You can actually see it if you look.
The eyes. Let me see like shadows.
You can see the shadows. Those shadows are all trickery. Now, if you want to see an extreme example, there you go.
Oh.
That is the same sphere. Now, how do I know that this thing was normal mapped as opposed to deforming the geometry? Look at the sphere. You can see that this thing looks like it's this nasty rock asteroid kind of thing, but look at the outside of that. Oh, how pretty. It's a perfect circle, right? So clearly I could look at this and say that thing's been normal mapped. They're using all of these lighting tricks to make it look like it's not lit in certain areas, right? That's a pretty powerful technique that you need to appreciate. All right. Question. Somebody had a comment. Yes. No. Oh.
I was just helping him.
See,
I'm not understanding what normals are.
normals are pinheads.
Go back to that.
Yeah, we'll talk in a bit. I need to make sure I cover some graphics. But think of normal as if I have a plane, it's the thing that's perpendicular to it.
Okay, so it doesn't have anything to do with vertexes. More about like a plane.
It is on the vertex, though. So, for example, if you mind flipping on the lights real quick. So, as an example, if I were to draw a triangle up here, okay? So, 1, 2, 3, I draw this triangle right here. What's the normal of this triangle? That guy, right? It's a vector that's coming out of this triangle. But what about the vertex, right? So you can imagine this guy, and this guy. All three of these things have a normal of this.
So you just average their normals to find the triangle.
Yeah, you can do all sorts of stuff, but assume that each vertex has its own normal. The reason that that's important is because if you have a circle, or I'm sorry, a sphere, you can think about each one of those things is going to have this pinhead look to it, right, as we go around. So it's a vector that's coming out of the vertex.
I suppose I'm kind of confused about how something can have something perpendicular to it. It's just a point. It's just an equation.
Just assume that it does. There's magic.
I mean, it's no wonder.
We'll talk later. If you understand the concept of a normal being this vector that's coming out of something, then that's where you start. Right.
Just need to know the book.
Also, flip the lights just real quick, just to see some extreme stuff. This is beautiful. I've only seen a couple of examples of doing this. There's things called like parallax mapping, and so you can see right here, as you go around this, it actually deforms the texture to make it look like there are these huge crevices. Believe it or not, you've got two planes that are right there. That's it. And as you go up to it, you can actually see the geometry move back and forth, but it's all just changing where the texture coordinates and stuff are. Beautiful. It's awesome. Fantastic stuff.
It sounds really hard to do.
I've seen the code for it, and it's really not that long. You will not be doing this in the computer graphics course, if it makes you feel better. Okay, so do we need to do some code? Yes, Jeff?
Of course, Jeff.
We love code. Oh, crud. Let's take that back.
Where do you find examples for stuff like that?
The new diet, there's clearly a virus.
Yeah.
So the question was, where do you find examples of doing this? I would, before you dive and start looking around for examples, make sure that you have the foundations there first, and then honestly, you type in parallax mapping in Google, and you see what it pulls up. A lot of books, graphics books, will have that technique in it, and at least you can understand the concept. Okay, so let's code. You guys help me out. I think last time it was a disaster when we tried to do this. But let's see if we can recreate a disaster.
Yeah.
So I'll save this file here, and we'll go, where's downloads? You guys help me out. Show all downloads, so we'll leave that there. Let's pull up some XNA. And in fact, there's the old one. Do we want to recreate it? Okay, so as you're going through this and you're doing your assignment, your 3D assignments, you probably want to watch this video. We'll call this Dragon 2. Hey, let's spell it wrong. Dragon.
Dragon.
Oh, sure. Dragon 21. Why not?
Dragon 21. XX.
That's how much I care.
XX
All right.
Dragon 21 XX.
Yeah. Okay. Underscore dot slash.
Slash 420.
420.
Okay, so it is going slow. All right, so it made the project. Let's grab our Dragon friend here. There's Dragon test. Where's Dragon 21? Here it is. In fact, let's move that guy over. So we open this guy up, find the content folder, move Dragon into Dragon, and that should be good. Come back over here, View Solution Explorer. My contacts are fuzzing over right now, so my apologies. Add an existing item to the content. You've got your Dragon. Remember, there is a properties here if you want to go to that and see if the importer is correct. The importer should be this Autodesk FBX. I think it's there by default. And then you can shut that down. It should be fine. Okay, let me remove some of these comments just to make sure you see everything that we don't need to do. Right, load content, we'll keep. Unload content. Does anybody use unload content? No? Okay, you guys are slack, just like me. Okay, so if I were to run this, let's make sure there's no problem with it. Control F5. We should have cornflower blue.
Yeah.
Yeah, hooray. Let's change that to black so that we can get some interesting things going on. I don't know why they chose it either, but it doesn't matter. Okay, again, remember there's no sprite batch begin, sprite batch end, none of that stuff because we're not working with sprites anymore. What are we working with instead? Okay, models. So model, I'll call it the Dragon model. Yeah, come on. Dragon model, and what else are we working with? Whoa. I affect matrices. Matrix. What three matrices are we worried about?
Model matrix.
Model matrix. What else?
Matrix. World matrix. No, view matrix.
Oh, wait.
View matrix.
View space matrix. Okay, we'll just call it the view matrix. What else?
That's it, right?
There's one more.
Oh yeah.
Projection matrix. Okay, so there you go. So we need to give starting values to these things. Right now we'll leave the view matrix and the projection. Well, no, we'll leave the view matrix alone, I think. Come down here. Let's load the model. So I can say Dragon model gets what?
New.
Nope, not new.
Content.
Content dot load. What are we loading? Model. What's it called?
Dragon.
Dragon. There you go. You've loaded a Dragon model. Believe it or not, one line of code. Can you guys see that okay in the back?
I don't have my glasses.
How about now? How about now?
A single pixel.
You must see. I wonder how large this will go. There, that's it. Okay. So what's the next thing I need to do? I need to assign the model matrix. Model matrix starts out as what? If we just want to get the Dragon onto the screen visible, what do I need to do? It's not the identity matrix. I'm glad somebody said that. What is the identity matrix? You do nothing. Right? That's all the ones down the diagram. That does nothing. Which is what we want our view matrix to begin with. Aha. We have to push the Dragon into the scene. And how do we do that? We have to do a translation, but along the negative z axis. I'm trying to tell you this so that you know mentally the first thing you want to do is to push that Dragon into the scene, or push the objects into the scene a little bit so that you can see them. So how am I going to do that? I think I say matrix.create translation. It wants a vector 3. But watch, it's overloaded. So I can just pass it. Where is it? X, Y, and Z. That looks pretty good to me. How far on the X? 0.0. 0.0, right? And then what's the third one? Negative, yeah, let's try like -2 or something like that. Now realize that this is going to depend on the scale. If you are trying to import your own models, you may have something and the modeler created it 10,000 scaled big, and I'm not joking. A lot of models are this way, or they did the opposite, where it's 0.001 scale and all this weirdness. So what I would recommend is that in the real world, real practice, You take it into Blender, you take it into Maya, something like that, and you scale it so it's a unit size, so that everything is basically the same size. Does that make sense? You're going to see some weird stuff if you start putting your own models in your project, which I encourage you to do, by the way. Okay, so that's the model matrix. What's the next one? The view matrix. Gets what?
That was the identity.
Matrix, yeah, we'll do the identity here. And then what's the projection? We'll say projection matrix gets matrix. Oh, come on. Dot create perspective field of view. Okay? Now, again, let's talk about the options that are here. You should be familiar with some of these. The first one is the field of view, which is what?
How much you can see.
Yeah, how far out it is, right? So if you want a sniper rifle, do you have a wide field of view? No, you have an exceptionally narrow field of view. In fact, if you want to add a sniper rifle in this assignment, that would be a great way for some extra credit. What do? You just set the view matrix to be something that has a really narrow field of view, and all of a sudden, boom, you're looking in and you've got a sniper rifle. Okay? So the field of view is going to be what? 60. What's the problem with putting 60?
It's a weird number.
It is in radians. In fact, it even says it on the screen, in radians.
Pi divided by 3.
Pi divided by 3, which is what? 1.0. Fine. I don't care. Aspect ratio. What is this? 800 divided by 600. And why am I putting the .0f and all that stuff? If you don't do that, it's going to divide into an integer, and you're either going to get 1 or 0. Be careful. Okay, near plane. What is the near plane? What I don't want you to do is just to say, yeah, I'm going to copy what Jeff put. That's a really bad idea. I want you to understand the concepts. The near plane says it's the cutoff. Anything closer doesn't get rendered. And what about the far plane? Anything further doesn't get rendered. So 0.1 and then 1,000. 100 is fine. I don't know if it's going to fit on the screen. There you go. Ah, crud. Okay, so we have our matrices set up. What are we going to do in update? Nothing. What are we going to do here? This is the one I think I slaughtered last time, so you guys help me out. Yes, for each model mesh, we'll call it mesh, in dragon model. Okay, that's the first loop, because remember, we could have a whole bunch of meshes that, a piece of arm and a face and a nose and all this kind of stuff. And then, excuse me, for each, I'm going to die here. Basic effect, B, in, is that right? Mesh.effects, I think. But yes, mesh for the most part. What are we going to do? B dot, and then this is where we're going to set our matrices. So is it world gets, what did we call that thing? You guys help me out. Model matrix, there we go. B dot perspective, or what is it, projection? Projection gets what? Projection matrix, and then what's the third one? B dot view gets view matrix. There we go. And then also I'm going to say B dot enable default lighting, and I can't remember, is that a method? Yes, it looks like it is.
For each loop, you need a dot mesh or something.
Let's try it. Probably. Come on. Dots. Meshes. Does that look? Come on, baby. There we go. All right. So what's going to happen? I don't know. Let's run it.
Magic.
Oh, wait. No. We did this last time. I always forget that. Right here, what do I say? Mesh dot draw. Oh, yeah. Okay. There we go. And we have a dragon. Okay, so we're at the point now. We have about 8 minutes until class is over, right? So what's the next thing that we probably want to play around with? Rotation. Okay, let's do a quick rotation just so you can see. If you want to make things rotating around, realize that you're changing the model matrix for that model. Does that make sense? We're not talking about us pushing our way through this environment, looking around at the birds and bees and all that kind of stuff. We're talking about something that's just spinning around or moving around the environment, something like that. So what are we going to do? Let's create a quick float rotation, something like that. 0.0 inside of update. We'll say that the rotation plus equals, 0.01, something like that. What's the next thing? We have a variable that tells us how far we should spin around, but what do I need to do?
You need to rotate it first.
Change the model matrix. Okay? So one of the things that you're going to be tempted to do, in fact, we'll just do this the correct way, matrix.create rotation y, and pass it rotation. Okay?
So you don't have to actually create the matrix.
We do not have to worry about any of the matrix math even, which is great, right? You had to worry about it for the midterm, but not there. Okay, so look at what we're doing. We're changing the rotation. We're updating that model matrix, wiping out, pay attention, wiping out the old matrix that was once there. Does everybody get that? So what was previously there, a little bit of rotation, that's gone, and we create an entire new one and put it here in the model matrix. So what's going to happen the next time it's drawn?
It's going to do that.
It's going to use that new matrix, and then the next time it updates, it gets a little bit more, and then it's, it's wiped out everything else, and then we're going to constantly do that loop. That's an important concept because it's going to help us. Whoa. Oh, yeah, what happened?
Forgot to move it.
I forgot to translate it. Okay? So what do we want to do first? Translate or rotate?
Rotate. Rotate.
Rotate and then translate. So watch how we do that. If I want to combine things together, times equals, create, translate, 0, 0, 0, negative 2, something like that. That's fine. And we get a rotating dragon. Okay?
It's beautiful.
It's beautiful. Now, the next question is, how do I move through the environment? Let's make sure you understand what's happening with that model, because when we talk about the view, these two lines, hypercritical, right there. See those guys? Because the first thing that we do is we say the model matrix is going to start out as just a plain old rotation matrix. There's not a whole lot of information there. Then what we do is we do matrix multiplication. We're taking one matrix, multiplying it by another matrix, and then overriding the model matrix. So everybody get that? So we're basically combining these things together and updating the model matrix so that it has both a rotation and a translation. You with me? That's how that thing works. Now, what if we wanted to start moving around in the environment? So we've got a spinning dragon, but now I want to be able to walk around.
Change the view matrix.
As you press keys, have it move.
Okay? So how am I going to do this? I'm going to change the view matrix, right? Because right now it's the identity. So how am I going to move around and all that kind of stuff? In fact, let's say that I have WASD, and I don't know if I'll be able to pull this off in time, but let's try it. If keyboard.getState .isKeyDown keys .a, what are we going to do if they press the A key?
We're going to move it.
View matrix dot create.
View matrix times equals
Matrix dot create.
create, yeah, matrix
Create transition.
dot create
Translation.
rotation.
Rotation.
And it wants the number of, let's see, as negative 0.01f, something like that. Okay, this is hypercritical. What we're saying, when I see this times equals, it's the same thing when working with a single variable. What does times equals do?
It multiplies it and adds it.
It's the same thing as saying view matrix get view matrix times this rotation matrix. I'm combining all of this stuff. Watch the difference, because I'm going to wipe this out in just a second. I should be able to run it. Where's the F5? Right here. Okay. That's the only key that works, and I can push it off of there. Now I'm starting to look around. Hopefully this will work. See if the, there it is.
There it is.
Okay. So I'm spinning around my view. Okay. What about the D key? If I run it now, sweet equals true.
Yes.
Okay. What about forward and backwards? What wouldn't I need? Oh, I need.
And then I was thinking
Create translation. I'd say 0, 0,
Zero.
0, negative.
0,
Negative.
negative 0.01.
Yeah.
Okay.
Mess around with numbers.
Numbers are so.
And then A? No, sorry, S would be a positive. Okay. There's something very important to learn here. Okay. I look this way. In fact, I'm going to stop this stupid thing from rotating. It's confusing. And if I were to run it, I can go forward and backwards. Does everybody see with that? I can look left and right. Now watch this. This is an important concept right here. I should be able to go over here. Oh, I'm going the wrong way. I've got the keys backwards. I did something stupid. And if I look over here,
Oh, it's the triangle of it.
what I'm doing is I'm walking over to the side. The lesson that you need to understand, and this is what's going to hit home, is that if I keep the old view matrix and I'm looking this way, or how about this? Let's say that I'm starting out this way. I'm directly down the z-axis. If I take the old view matrix and I multiply it by a translation down the z-axis, what's going to happen? I'm going to go down the z-axis a little bit. I keep doing that, and I keep doing that, right? Now here's the cool part. If I multiply now by a rotation matrix, and let's say I'm over here and I'm looking at this direction, 45 degrees, something like that. If I multiply now by a translation along the z-axis, what's going to happen? I go off in this direction. Okay? It's going to be temptation. I guarantee you there's going to be 3 or 4 people in here that go out there and they try to have an individual x, y, and z variable. They try to have an individual rotation about the x, y, and z, and then they try to make some foobar trigonometry, something or other that's going to go. It's not going to work. And the reason is because you think about it. If I'm going off and let's say I'm rotating in this direction and I do this, the way that you're going to do it is if all of a sudden I press the right key, you know what's going to happen? I'm going to go like this. I'm still facing in this oblique direction, and I'm going to go off down the x-axis. I guarantee you some of you are not paying attention right now. You're going to try to hack some crap out, and it's going to be awful. Okay, so if you think about it, these view matrices store everything that you need. They store a translation. They store a rotation. They store scaling and skewing and all of these kinds of things. Everything that you'll need is going to be in one matrix for the view matrix. And believe it or not, if I aim up and I go along the negative z-axis, what's going to happen? I fly. Flight simulator. If you want to make a flight simulator, you can. Watch this. Last thing that I'll show you. What if I was messed up and I did this?
See what happens.
Or something like that. Now I had a variable or something like that. What's going to happen?
It won't move.
It's not going to move. Well, where's F5? I can barely see it. Okay?
Just going to
Look at that.
constantly reset it to the same thing.
Yeah, there you go. You'll get partial credit, maybe.
Just press the key.
But think about it. You're aggregating all of that stuff into that matrix. That's the main idea. And it's turning a little bit, and as soon as you say translate along a coordinate system, a particular axis, it's whatever way that camera is facing.
That is
Yes? It is awesome. But it's confusing the first time you go through it. So if you get stuck, let me know. There's no class next week, right? Right. What are you supposed to do? Work on the project. If you want to spend some time on the 3D, you can too. Any questions before we go? No. So if somebody could flip on the lights, I would appreciate it. And you guys have a good week, and I'll see some of you at Siege.